So yesterday we finished calculating the, we finished calculating the a process in which an electron and a positron annihilated in creating a muon and an antimuon. Is that the one we calculated the cross section for? Yes. So let's write down the amplitude for that. So we had an electron coming in and a positron coming in. So this is the only Feynman diagram at the tree level. And let me just, for the time being, use a different color for the muon. Not that it matters. So the matrix element for this is, so I'm just going to redo this so that we can have more practice. I'm sure you guys are as expert in this by now, but it's worth redoing. So we go against the arrow for the electron. So we have a V bar S2, P2, and then let's call this vertex mu, this vertex nu, and then we have a vertex factor E minus IE gamma mu, and then we have the electron spinor wave function. And then we can just consider the photon propagator, which has momentum P1 plus P2, which is our Mandelstam variable square root of S, except that this is actually a 4-vector now. So the photon propagator, you've chosen a gauge, the Lorentz gauge, in which and then we come to the muon line, and the muon line gives us and then we can sum over the final spin states and average over the initial ones. And because there are two initial particles, the averaging factor is 1/4. So if you do this, then we get a nice and easy, formula, which is and here you have to, we assume that the mass of the electron was much, much smaller than the energies involved, so we could ignore the mass of the electron. Now, in this theory of QED, where we had electrons and muons and the antiparticles, we could have had another process in which we can scatter a muon with an electron. So this is our muon. and an electron is coming in and going out. And they're exchanging a photon. So if we calculated this thing, the matrix element we would have gotten, let's consider the electron line first. We have to go like this. So we have a U bar, because it's an electron, R1 prime, P1 prime. Let's give these guys label, mu and nu, or, yeah, it doesn't matter. Then minus I epsilon gamma nu. And then an electron is coming in, so we have to put another factor of U here, US1 P1. And then we put the photon propagator. So the momentum going that way is P2 minus P2 prime. So this is, if you remember from our lesson on Mandelstam variable, is, I think there's a minus I here, I've forgotten, is T from our STU variable. And then we come to the muon line. And for the muon line, we have U bar R2 P2 minus IE gamma mu. There's another U, S2 P2. Maybe there's a prime here. Okay, so, and then we can do the same thing where we sum over an average, sum over the final state and average over the initial states. And the details are given in the notes, and I'm not going to do this. And then you can use the gamma matrix identities and simplify that result. And when the dust settles, you get something that looks like this. Right. Sorry, I've written all of this in the orange letter. I don't mean this whole thing coming from muon. I should have, anyway. So if you now stare at these two diagrams, you realize that if I didn't specify which direction time went, they look very similar. If you look like this, if you look like that, or like this, I guess. Yes. So you might ask the question if they are somehow related. And it turns out they are. So if you took the positron and an anti-muon in the first diagram, say the thing that is coming from below and the anti-muon which is going out below, and made and changed them to an electron going out and a muon coming in, right? Then that diagram would map to that diagram. Okay? So it turns out that this is actually a general property of amplitudes, that if you take an amplitude in which you have some particle in the initial state of momentum p going to some final particle, then that amplitude is equal to, formally, the amplitude that you would get if you wrote the antiparticle, if you wrote the amplitude for a process in which the antiparticle of that particle was in the final state, but with momentum minus p. For momentum minus p. Now it turns out that when you flip this, these guys are never in this. One is physical, the other one is never physical. And what I mean by that is that your P0 for this guy has to have some positive energy, right? Whereas for that guy, this P0 is negative. The P0 component of this momentum is negative. But the analytical formula is given by this. So for the case of fermions, one also has to do something to the spin states, the helicity states, which I'm not going to go into. I'm just telling you this and I'm proving you this. And the way that we apply this formula to our case is that we take our positron in the initial state and we replace it by an electron in the final state. We do two replacements. So we use this formula twice. So if you do this, of course, what I'm just going to do this in this average and summed over final the matrix element squared, so I don't have to worry about the spinner part, the helicity part. So all I have to do is just replace the momenta. So if I do this in our first amplitude, then our first amplitude becomes, you can verify, it's P1 minus P2 squared. Remember, this was S of STU. The S consists of P1 plus P2. Now we have P1 minus P2. And inside, you get P2 dot P1 prime, P1 dot P2 prime, plus P2 dot P2 prime, P1 dot P1 prime, and then the sign flips here. All right. So now, if we now relabel P2 to P1 prime, this is just relabeling, there's nothing deep here. If I were, then you can show that, you can see that this is exactly this. So indeed, my claim that by making these substitutions, I derive one amplitude from the other. And let us go back again to the observation that we got the second amplitude from the first amplitude by replacing P2 by minus P2. So in the second amplitude, for the second process, we expect P2 0 to be positive. We also expect P2 prime 0 component to be positive. But here we see there's a minus sign in front of these two things. So by making that replacement, what we are getting is we are getting a formal expression for the amplitude for the which is equal to the second process from the first process. But to actually claim that that amplitude is the amplitude for the second process, we are evaluating it in a different part of the value of air momentum. So if you think of this amplitude, you can think of this amplitude as a function of the momenta as analytic functions of momenta. You can think of the momenta as, say, some complex variable, and these two different amplitudes are essentially that function of complex variable being evaluated at different parts on your plane. Okay, so using this analytic property to relate the amplitude of different processes has a name, and it's called crossing symmetry. Crossing symmetry also plays an important role in the LSZ formula. And the way it does is that, remember what the LSZ formula does is that it takes you calculate formally, whether you can actually do it in real life or not, that's a different question, some endpoint function, right, of the vacuum. And somehow you extract from this the S matrix element of some particular process. And there's some time ordering here. Now, whether this has two particles coming in, a physical process that you're interested in, n minus 2 particle going out, or 4 particle coming in, and n minus 4 particle going out, you use the same vacuum correlation function. It's just that the LSZ formula picks out different S matrices from this correlation function. So in some sense, the underlying object is one analytic function from which the LSZ formula picks out different amplitudes for different physical processes. So this assumption of analyticity is there, in the LSZ formula. Okay, so it's and here I'm showing it in a more manifest way. Okay. So far, we haven't really done any Feynman diagrams which considers a photon in a final state. In yesterday's tutorial, you saw an example of that, but I gave you what the spin-summed average amplitude squared was, right? So there's another piece of information you need to compute those things. And that's our next topic. It's called polarization sums. So suppose we have some process so with a photon in the final state, in the external states. So that amplitude will have some label, which is the label of the polarization of the photon, right? So suppose the photon polarization is E of lambda mu. This is the polarization. Then we can label that amplitude by m of lambda. And we can factor out the polarization part of it. So M mu, we are factoring out the polarization part in this way. Now, if you are interested in some experimental setup where we are summing over the final polarization states, because like in the case of electrons, a lot of our experiments won't be able to detect the polarization states of the final photon. And we might not be able to create a polarized beam as well. So we have to, so like in the case of the electron, we'll have to sum over the polarization states. So we have to consider this kind of averages, sums. Okay. Now the problem is that there is no nice formula for summing over just the two polarization states. Remember that when the space of polarization is four-dimensional a priori, and we had some polarization sums there, which was say 0 to 3, and that had so we had lambda of mu star, lambda of nu, and we had some lambda lambda prime, and that gave us something like eta mu nu, right? But here the sum went from 0 to 3. So we can't use that here because the sum only goes from 1 to 2. Because the physical polarization, which the external photons will have physical polarization only. So it'll only have 1 and 2. The 0 and 3 won't be there. So how do we deal with this? So you can show, although this is not the way we'll show it, and I will show it in a different way, that this thing, when you express it in the Heisenberg picture, has a form like this, where J mu is our current that is conserved, and I and F are states, external state, without the photon part, without the photon in question. But K is the photon momentum. It then follows that from the fact that your current is conserved, so if your current is conserved, and that is also true quantum mechanically, then in quantum field theory we can write equations like this. So this is just saying that the quantum version, when you quantize your theory, your conserved current is still conserved. And in the supplementary lectures, I will prove these sort of, I will show you how to derive these identities in one of the tutorials. And this is called the Ward identity. And the right. Yeah?
What does it say next to I? F external states with.
Yeah, external states without the photon in question. So I and F, these guys have all the other particles in the external states, but except the photon that we are talking about.
All right.
Okay? So, so this implies that when you contract the amplitude mu with the photon, then this is, this gives you a, that this is 0. This is nothing but the Fourier transform, the momentum space version of this equation. Okay. Another way of showing this, okay, let me just tell you what the consequence of this is, and then I'll show you another way, a more sort of obvious way of arguing that this is going to be true. So if this was true, well, you can prove that this is true. Let's choose an example where our momentum of the photon is along the z direction. Then what this equation tells us is that the 0th component of m is equal to the 3rd component of m. And then what we can do is that we can then take this sum, polarization sum, which goes from 1 to 2, m lambda star, m of lambda, and then we can decompose it in terms in this way. And then my claim is that that sum can now be extended from 0 to 3 where we have chosen the the 0th polarization to be this, and the 3rd polarization vector to be this. Because we know that these guys are, if we chose these two to be like that, and with the other two choices, canonical choices, this is true. So why can we write this? Because in this sum, the 0th component and the 3rd component cancel each other out, right? Therefore, this sum is actually the stuff that really contributes to this sum is only the 1 and the 2 component.
So we must be careful that when we are averaging over polarization, not to write the things in the center of mass frame, but in the frame where where the photon has that specific one specific K?
No, it should be a frame-independent statement.
Right.
I'm just showing it in one particular frame.
Okay.
You know that one of the nice things about having tensorial expressions is that if you can write it in one particular reference frame, it's true in any reference frame, right? So, you know, in extending the sum from 1 to 2 to 0 to 3, what we are essentially using is the fact that that M, when contracted with a null vector, gives us 0, right? And we saw that the way this is organized is that that the 0 part and the 3 part, the polarization vector actually is organized as a null vector, right? So another way of seeing that this must be true is to argue from gauge invariance. So now recall that if I take our basis, plane wave basis, and then we make a gauge transformation. So under a gauge transformation, this changes in this way. Now, if we are in the Lorentz gauge, then chi, we found that chi has to satisfy this. And that means chi can be written as some function of this form. So if you make a gauge transformation in the Lorentz gauge, what happens is that our polarization vector changes up to a vector that is proportional to k, up to a term that is proportional to k. So if this is the case, then the amplitude that we wrote down, which was, say, we wrote it down in this form. Sorry. So under a gauge transformation, this would pick up a new term, right, which would be, say, I k mu f of k, this. So our amplitude will not be gauge invariant unless, so our amplitude will not be gauge invariant unless k mu m mu was 0. Okay, so this is another way of arguing that this thing must be true. As our last example, as an application of this, let us do, well, of some of these ideas, let us do an example of Compton scattering. So Compton scattering is the process in which an electron, a photon and an electron scatters. So an electron is coming in, and a photon is coming in, and it has some polarization, and then the photon is going out. So it's a scattering of photon and electron. And there are two diagrams at the tree level. One is, in this diagram, the photon is absorbed and then it's re-emitted. In another diagram, the photon is emitted first, so the Q prime photon is emitted first, and then the Q photon is absorbed. Okay. So these are very easy. What is the amplitude? Let us write the amplitude. For the first one, we go like this. So we have a U bar, S prime, P prime. And let's call this mu nu. And say mu nu. And then we we can finish the fermion line, but let's just insert a photon. So it's an outgoing photon. So we have an E star of nu Q prime. And there's a vertex factor minus E gamma nu. And now there's a propagator, and I just realized this is P plus Q. The P plus Q is missing from my notes. The app that I used to write it seems to have gobbled it up. Anyway, it is P slash plus Q slash plus M. This is the fermion propagator. So P plus Q whole squared plus, minus M squared. And there's a plus I epsilon. And then we come to this vertex. And there's there's a vertex factor for this. And there's an incoming photon here. So there's a polarization vector for this, which is E of Q and nu. And then the incoming electron wave function. Okay. And then another similar term. And we have lots of time, so let's just write it out. Again, U bar. These things don't change. But now the polarization vector is the vector for the incoming photon, so no star here. So nu of Q minus I E gamma nu. And then we have the momentum going here is P minus Q prime. So here we have I P slash minus Q prime slash plus M by P minus Q whole squared minus M squared. And then we come to this part. And here first we have an outgoing photon. So epsilon star of mu of Q prime. And then there is a vertex factor, i.e. gamma mu. And there's an incoming electron, so it's a U bar P of S.
The first line should probably epsilon mu.
Yes. Yeah. Good.
And in the last U,
Oh, yeah, right. Yeah. All right, so
In the electron propagator, is the I only multiplied with P, or does it multiply with Q? Sorry, the P slash, or does it multiply with Q slash as well?
sorry. Oh, yeah, that's very good. It's actually, the I is outside. Now, like we saw there, if you now make a gauge transformation, what happens is that our polarization vectors change by a null vector, by a vector that is proportional to either q or q prime. So under gauge transformation, epsilon, these guys shift by either a q prime or a q. So the new terms that you pick up in this amplitude are can be just, the way to look at those terms is to just replace these things. Say, replace E mu star by, say, Q mu prime, or epsilon mu by Q mu. And then you can do a simple calculation, and you can show that the contribution from this and this will cancel each other. So the gauge invariance is present at each order in perturbation theory when you take into account all the diagrams that are present at that order, which can also be seen as a consequence of the word identities. So the word identities actually tell us that the gauge invariance is present even at the quantum level at each order in perturbation theory.